Ever wondered how everything around us is interconnected? Absolutely, the concept revolves around systems and environments. In the fascinating domains of physics and chemistry, the term system is employed to signify a specific segment of the universe on which our attention is directed. It can be as minuscule as a solitary atom or as intricate as a sophisticated apparatus, extending to the vastness of an entire ecosystem. The surroundings, in contrast, embody everything that exists outside the system but maintains the potential to interact with it. Such interaction could manifest in various forms. It could be the transfer of energy, exemplified by heat conversion or work, or the transfer of matter, like the exchange of gases nature between a plant and its surroundings. The state or condition of a system, whether that refers to its temperature, pressure, or volume, is directly impacted by its interactions with the surroundings. These interactions are far from trivial. In fact, they lay foundation of numerous natural phenomena and scientific principles that govern our world. They unravel the mysteries of energy interchange, matter transformation, and the fundamental principles of nature's workings. A proper comprehension of a system and its surroundings, therefore, is not just a mere academic exercise. It paves the way to truly appreciate and understand the science of thermodynamics. Understanding a system and its surroundings is the first step towards understanding thermodynamics. Now let's get into the heart of the matter: work, heat, and energy. Work, in the simplest terms, is the force that causes an object to move. Heat, on the other hand, is a form of energy that flows between two bodies due to a temperature difference. Now, energy is a measure of the capacity to do work. It could be kinetic, potential, thermal, chemical, or even nuclear. These three concepts are interrelated and fundamental to the study of thermodynamics. For instance, when you push a block, you're doing work on it. This work can increase the block's kinetic energy or heat it up due to friction, thus showing a relationship between work, heat, and energy. Understanding these concepts is like learning the alphabet before writing a poem. They are the basic building blocks you need to grasp the more complex principles of thermodynamics. These concepts of work, heat, and energy are the building blocks of thermodynamics. Let's now delve into the properties that define a system: extensive and intensive properties and state functions. First up, extensive properties. These are properties that depend on the amount of matter in a system. Think mass, volume, or total energy. More matter means more of these properties. On the other hand, intensive properties don't depend on the amount of matter. Temperature, pressure, and density are a few examples. Whether you have a thimble or a bucket of water, its boiling point remains the same, right? That's an intensive property. And what about state functions? These are properties that only depend on the current state of the system, not how it got there. Energy, pressure, volume. These are all state functions. They help us understand the system's behavior without needing to know its entire history. Knowing these properties helps us predict how a system will behave under different conditions. Now let's discuss the first law of thermodynamics. This law, also known as the law of energy conservation, states that energy cannot be created or destroyed, only transformed. It's like a cosmic rulebook for energy, dictating that the total energy in the universe remains constant. Within this law, we find two important concepts: internal energy and enthalpy. Internal energy, denoted as U, is the total energy contained within a system. It's the sum of the kinetic and potential energies of all particles in the system. Enthalpy, on the other hand, denoted as H, is the heat content of a system at constant pressure. How do we measure these, you ask? Well, change in internal energy can be calculated by subtracting the initial internal energy from the final internal energy. Similarly, the change in enthalpy can be calculated by subtracting the initial enthalpy from the final enthalpy. The first law of thermodynamics is a fundamental principle that governs all physical and chemical processes. Have you heard of Hess's law? Let's explore this interesting concept. Hess's law, or the law of constant heat summation, is a fascinating principle in thermodynamics. It states that the total enthalpy change in a chemical reaction remains the same, irrespective of the route by which the chemical reaction takes place. Now, let's delve into the various types of enthalpy. Bond dissociation enthalpy is the energy needed to break a bond in a molecule. Combustion enthalpy, on the other hand, involves the heat released during a combustion reaction. Formation enthalpy is the heat change when 1 mole of a compound is formed from its elements. Atomization enthalpy refers to the energy required to convert a compound into its constituent atoms. Finally, sublimation enthalpy is the energy required to change a solid directly into a gas without passing through the liquid phase. Hess's law and enthalpy give us a deeper understanding of energy changes during reactions. Finally, let's discuss some important processes: phase transition, ionization, solution, and dilution. Phase transition, simply put, refers to the change of a substance from one state to another. We observe it every day, like the melting of ice into water or water boiling into steam. These transitions occur when energy, in the form of heat, is added or removed. Remember that during these transitions, the temperature remains constant until the entire substance has completed the transition. Next up, we have ionization. This is a process where an atom or a molecule acquires a negative or positive charge by gaining or losing electrons. Think about the sodium and chlorine atoms in table salt. Sodium gives up an electron to chlorine, becoming a positive ion, while chlorine becomes a negative ion. This exchange of electrons leads to the formation of ionic bonds, like the one in our everyday table salt. Now let's talk about solutions. A solution is a homogeneous mixture of 2 or more substances. The substance that gets dissolved is the solute, and the one that does the dissolving is the solvent. A classic example of a solution is salt water, where water is the solvent and salt is the solute. This process of making a solution is important in many chemical reactions and in the creation of many products, from pharmaceuticals to your favorite soft drink. Lastly, we have dilution. It's the process of reducing the concentration of a solute in a solution, usually by mixing with more of the solvent. For instance, if a juice is too concentrated, you might add water to it. This would be a dilution process. All these processes, phase transition, ionization, solution, and dilution, play a critical role in the field of thermodynamics, allowing us to understand and predict how substances will interact under different conditions. These processes illustrate the practical applications of the concepts we've learned in thermodynamics. Well, that's a wrap on our crash course on thermodynamics. We've covered a lot of ground today, from the basic concepts of systems and surroundings to the intricacies of work, heat, and energy. We've dived deep into the extensive and intensive properties and state functions. We've also unraveled the mysteries of the first law of thermodynamics and Hess's law. We explored the enthalpy of various processes and delved into phase transitions, ionization, solution, and dilution. All these concepts are crucial in understanding the physical world around us, and mastering them will open the door to a whole new world of scientific exploration. If you found this video helpful, don't forget to like, share, and subscribe to Facts Academy 0122. Your engagement helps us create more content like this. And if you have any questions or comments, feel free to drop them below. We always love hearing from you. Thank you for watching.